Oops. Hi guys.
Good morning.
How are you?
How are you? I'm good. How are you?
Good, thank you. Get everybody else in here. So I was talking with your classmates in the 8 o'clock class about our quiz on this coming Thursday, and our homework that's due in this coming Thursday also. And give me a sec. When I set up the timing, when things are going to be due and what topics are going to be covered, I forgot that Wednesday we do not have class. We don't have class on Wednesday. So since we don't have class on Wednesday, that means that we cannot go over the homework for chapter 4.1 on Wednesday like we normally would. So I think what I'd like to do, if this is okay with you, I think it will be, is to change our quiz from including 3.5 and 4.1 to just 3.5. Okay, so the homework that'll be due on Thursday night is 3.5. The quiz that you guys will be assessed for is 3.5. I have to go in. I think I have to go in and change the due dates for the homeworks, but if that's okay with you, I think it will be. But we can move 4.1 to be quizzed next week, okay, instead of this week. Does that sound reasonable to everybody?
Yes, that sounds good to me.
Okay, wanted to make sure. I figured it would be. But given that, does anybody have questions on the homework for 3.5? There are 2 questions that I definitely want to cover to make sure, but I'll open it up to you guys first to see if you have those questions. So homework for 3.5, can talk about for a little bit. All right, I'll let you guys look it through, think it over. I'm gonna do a couple questions because I want to call your attention to it. Good, great, you guys are asking similar questions. So let's talk about, let me do the questions that I wanted to show you because it's included in some of these here, the ones that you're putting into the chat, and then I'll go on to the other ones that are in the chat. So this is chapter 3.5 homework that we're going to talk about. Okay, oh, is that focused? Let me just make sure this is all. I hate it when it does that. It makes it not focus. There. Okay. All right. So we're going to do, I want to do question 1 and I want to do question 8. They're kind of like 2 sides of the same coin, or 2 separate coins, depending on how you think about it. All right. So question 1 says we've got the limit as x goes to 1 of x to the p minus 1 all over x to the q minus 1. Okay. So now this is, right, we've got x, p, and q happening here. So what's the variable of note, right? So x is the thing that we're asking about for the limit. So we can assume this whole thing is a function of x, which means p and q are probably, you know, like some kind of constant terms. We don't know what they are. So since it's a function of x, I'll just assume p and q are just like regular polynomial exponents, right? So let me just do a quick check, right? Because we always have to check first to see that we're in indeterminate form. Because if I do L'Hopital's rule on something that's not an indeterminate form, I'm going to get the wrong answer. Okay, so I'm going to do my quick check. So as x goes to 1, so this is 1 to the p minus 1 all over 1 to the q minus 1. 1 raised to any power is equal to 1. 1 raised to any power is equal to 1. So we're dealing with 0 over 0, right? Which is an indeterminate form. I can't tell if, is that going off the page or can you guys see that? Okay, sort of. Hang on a sec, let me zoom out a little bit. Is that better? Okay, good. All right. So we're dealing with indeterminate form here. So that means that I can do L'Hopital's rule on it. All right. So I have to specify. Right. So I've got an indeterminate form. I'm going to do L'Hopital's rule. While you're in Calculus 1 and Calculus 2, these classes, you have to show that it's indeterminate and you have to say what your next step is. Okay, as you move along in the higher level math classes or in your more complicated engineering classes, you don't have to specify, you can just jump in and do it. But for right now, we need to see that you know what you're doing. All right, so I'm going to apply L'Hopital's rule, which means I've got the same limit as before. Oh, sorry, x goes to 1. But this x to the p, right? So if my function, let's do it offline. So if f of x equals x to the p. When I go to take that derivative, right, I'm just doing the power rule. Okay, so this is, I take my exponent and I bring it down out front and I subtract 1 from my exponent. I'll put that in little parentheses here. So this is like x to the cube minus 1, x cubed minus 1. So 3 times x squared, right? That's an example. This 1 goes to 0. I can do the same thing here for q, x to the q minus 1. Okay, so we've done this. Now we have to do our check again just to make sure, are we still in indeterminate form? Yes or no? If we are still in indeterminate form, I'm going to do L'Hopital's again. If I'm not in indeterminate form, I'm just going to evaluate my limit. All right, so we're going to check again. So as x goes to 1, I've got p times 1 raised to the p minus 1. I've got q times 1 raised to the q minus 1, right? 1 raised to any power is just 1. 1 raised to any power is just 1. So I'm dealing with p over q. Now, I guess technically speaking, I need to say q shouldn't be equal to 0 or whatever. I'm going to leave it like this. They didn't tell me anything about what p and q were. I'm just going to leave it. Okay. Because if q is equal to 0, then my limit doesn't exist, right? Or whatever. So right now we're just going to leave it like that. So that's question 1. It's basically a polynomial question, but we used variables for the exponents to make you think about what you needed to do. I want to contrast that with question 8. Question 8 looks like this. The limit as u goes to 0 of 2 to the u minus 4 to the u all over u. Okay, so now watch what's happening, right? I have an exponential function. These two are exponential functions, right? Instead of x to the p, which is a polynomial, a power equation, a polynomial function like x squared, I now have 2 to the x, right? So it's an exponential function. So it's a completely different set of rules for how I do derivatives, remember? So let's do our check for indeterminate, right? So I'm going to evaluate. So this goes 2 to the 0 minus 4 to the 0 all over 0. 2 to the 0 is 1, 4 to the 0 is 1. So this becomes 0 over 0. This is indeterminate, right? Which means I can do L'Hopital's rule on it. Okay, so I can do L'Hopital's rule. My limit is the same. Limit as u goes to 0. Now remember, our rules for exponents for taking the derivative. I repeat the exponent, and then I multiply by the natural log of the base, and then I do the chain rule on the exponent function, du. Du is just going to be equal to 1 in this case. Same thing here. I repeat my, oops, sorry, that's a 4. I repeat my function. I take the natural log of the base and I do times du, which in this case is just equal to 1. Okay, derivative of the bottom is equal to 1. Okay. All right, so now let's go ahead and evaluate. Let's check it. We're going to check. So 2 to the 0 times natural log of 2 minus 4 to the 0 times natural log of 4. Okay, 2 to the 0 is 1. Natural log of 4. Okay, and you can clean this up too if you want. Natural log of 2 divided by 4, natural log of 1/2. I don't care. You can just leave it like this. Don't worry about putting it in, like make a decimal. You can just leave it like that. It's fine. Okay, but I want to call your attention to it, right? Because this is an exponential function. Question 1 was a polynomial function, right? So I still have to go through all the same steps in terms of checking for indeterminate form, but how I took my derivative was completely different, right? Because one was exponential and the other was a polynomial. Okay. All right. Let's do, I'm gonna work, okay, so number 12 is good. So we'll do 12 and then we'll just work our way up through the other ones. Okay, I'm gonna scroll up a little bit. So question 12. Question 12 says the limit as x goes to infinity of x times the tangent of 1 over x. So let's go ahead and do our quick check, right, like we always do. So if I plug in infinity for x, I'm going to get infinity times the tangent of 1 over infinity. So 1 over infinity is 0, right? Because it's 1 over super large number, so that goes to 0. So this is tangent of 0. So this is infinity times 0. This is one of those other indeterminate forms that we talked about, right? Where I've got a race. Which one wins out? Is it infinity or is it 0? So this is indeterminate. Okay, so with an indeterminate form, I can use L'Hopital's rule. But first, before I use L'Hopital's rule, I want to rewrite so that it's in the form of numerator denominator. So I'm going to write limit. This goes to infinity. It's an infinity tangent 1 over x to the minus 1. Remember, we did this trick before in our notes last week, right? Where we said, we're going to fake it. We're going to put it into the denominator, but this minus 1 says it really needs to be on the other side of the dividing line. So just a quick check, right? This is the same type of problem that we had before. Okay, so this becomes another one where this is 0 over 0, essentially, in terms of our indeterminate form. So I'm going to do L'Hopital's rule, okay? Which means I'm going to take the derivative, but then my limit stays the same. So I take the derivative of the top, so that goes secant squared of 1 over x. Now I have to do chain rule, so I have to take the derivative of 1 over x, which is going to give me minus x to the minus 2. Okay, I did that like a power rule, which is also my derivative for the bottom, minus x to the minus 2. Okay, these two, right, will cancel each other. It's removable, it's continuity, so I cancel each other. So now I'm left with limit as x goes to infinity of secant squared of 1 over x, which is secant squared of 0. So secant squared of 0, so you want to take a look, you know, if you're not sure, you know, take the secant of 0. Secant is 1 over cosine, right? 1 over cosine squared, so it's going to just equal to 1. Okay, so that's how you would handle question 12. Question 12 is a good question. Okay, and we'll take a look at 39 and 52 in just a second. Okay. But make sure you're always doing that check first for indeterminate form, because otherwise, you know, you could end up doing L'Hopital's on something that's not indeterminate. All right, so 39. So question 39. So question 39 says, let's see if I have it all written down. So f has a continuous derivative, and f of 3 equals 0, f prime of 3 equals 4. So we want to find the limit as x goes to 0 of f of 3 plus 3x plus f of, I remember this one, 7x all over x. All right, so this one's kind of like a weird logic problem in a way. So let me just start working it through, and then you guys can take a look at it. So I'm going to go limit as x goes to 0 of f of 3 plus 3x plus f of 3 plus 7x equals 2 times f of 3, which is equal to 0, and x equals 0, because f of 3 plus 0 plus f of 3 plus 0. So I plugged in x equals 0. So if x equals 0, 3 times 0, 3, so this becomes f of 3 plus f of 3, right? So it becomes 2 times f of 3. We were told at the beginning f of 3 is equal to 0. So 2 times f of 3 is equal to 0. Okay. So that's kind of how we're getting that one. So then this becomes the limit as x goes to 0 of x is equal to 0. So this is my denominator. This is the numerator. Right, so we processed the denominator and the numerator. So now we're basically dealing with the limit as x goes to 0 of our whole function is equal to 0 over 0, which is our indeterminate form. So that now we can use L'Hopital's in order to process it. So basically we took this, our original function, and we plugged in, we did our check. Right, so I did the check on the numerator, f of 3 plus 3x plus f of 3 plus 7x. I plugged in x equals 0, 3 plus 0, 3 plus 0, so I get 2 times, right? So that's how we got the 0 in the numerator. Obviously, I plug in 0 for x, I'm going to get 0. So I have an indeterminate form on my function total, okay, which means I can use L'Hopital's rule for it. Okay, so I can use L'Hopital's rule to process it. So, right, so I'm going to get the limit as x goes to 0. So now I've got my function. So I've got my chain rule, right? So I've got 3 of x. I've got, when I take the derivative with respect to x, I have to take into account my chain rule, which is 3, right? So I'm going to get 3 times f prime of 3 plus 7 times f prime of 7, okay, all over the derivative of x, which we know is going to be equal to 1. So this is going to be, now we know f prime of 3 is equal to 4, okay? So this is going to be, oops, sorry, 7 times f prime of 3, because we're also evaluating. Okay, so this is going to be equal to 3 times 4 plus 7 times 4, which is equal to 40. But let me tell you how I did this part right here. So if I go f of 3 plus 3x, and I take that derivative, I'm going to get 3 for my chain rule, f prime of 3 plus 3x at x equals 0. This is equal to 3 times f prime of 3 plus 3 times 0, which is equal to 3 of f prime of 3. So that's how I got this right here. And this is a 3, not a 7. Okay. 39. All right, let's talk about 52. Let me give you guys a chance to finish writing that, and we'll talk about 52. Okay. All right, so question 52. The question 52, let's see, I've got, I forget how the question was written. This is how I have it drawn out. Okay, so then P2. All right, so question 52. So I've got 2 particles, P1, P2. I was given coordinates of these particles. So I've gone out 1 minus t in the x direction, 0 in the y. I've gone 1 minus t in the x, and I've gone 1 minus e to the t minus 1 in the y direction. Okay, so this is y, this is x. Okay, so okay, we want to write theta as a function of t. You can kind of start to see, right? So what do I have? Right, it's a right triangle, which means I can use my right angle trigonometry. So if I only have the opposite and the adjacent, and I mean, I could figure out what the hypotenuse is, but the opposite and the adjacent are just given to me. So I should be thinking about the tangent, right? So my tangent of theta equals opposite over adjacent, right? So I'm going to set this up as opposite, 1 minus e to the t minus 1 all over adjacent 1 minus t equals tangent. So now if I want to get this as theta equals something, so I take the inverse tangent of both sides. I get theta equals inverse tangent of 1 minus e to the t minus 1, 1 minus t. And then that's my function writing theta in terms of t. Part B says at t equals 1, both particles reach this asterisk right here, okay? Reach the asterisk, see at what theta two particles collide. Okay, so we're going to go like this. The limit as t goes to 1 of theta of t. Okay, which is the limit as t goes to 1, right? Because we were given this of our function inverse tangent 1 minus e to the t minus 1 all over 1 minus t. Okay, so now we'll do our check, right? So I'm going to do my check. So I plug in t equals 1. So I'm going to go inverse tangent of, this is going to be 1 minus e to the 0 all over 1 minus 1. So this is tangent of 0 over 0. Inverse tangent of 0 over 0. So this, right, it looks like we're accustomed to kind of thinking our limit is going to be equal to that. But I've got this here. So this is indeterminate. Okay. At t equals 1. So I need to be able to do L'Hopital's in order to process it. Okay, so okay, so our derivative of our inverse tangent, let's see, how can I think about it? I'm going to go like this. So let's write it like this. So the limit as t goes to 1 of the inverse tangent of 1 minus e to the t minus 1 all over 1 minus t, but it's as t. So this is going to become, we're going to say the inverse tangent of the limit as t goes to 1 of 1 minus e to the t minus 1 all over 1 minus t. And then we're going to take L'Hopital's here. Okay. So instead of trying to come up with the mess of like inverse tangent stuff, we recognize that our limit is happening here. It's a function. It's a composed function. And that's where indeterminate form is, right? And so we can bring our limit on the inside and then process our inverse tangent that way. All right, so inverse tangent, we're going to do our derivative on the inside, right? So this is the limit as t goes to 1 of, I take the derivative here, I'm going to get minus e to the t minus 1, right? So my chain rule, okay, so I repeat my exponential, got the minus, my dt is a positive 1, okay, so it's all over minus 1, right? Because this is my derivative here with respect to t, okay? So now at t equals 1, I have to do my check, right? So I'm going to get the inverse tangent of, so this is going to be minus e to the 1 minus 1 over minus 1, which is inverse tangent of, so this is minus e to the 0, right? So this is let's see, minus 1 all over minus 1, which is equal to the inverse tangent of 1, which is equal to pi over 4. Okay, it's an interesting question. I'll give you guys a chance to finish writing that. Then we'll start chapter 4.1 with my 4.1 lecture notes, which I printed out, lecture examples, which I printed out. So you guys might want to print that out as well, or you can copy it down later. Guys all set with that? All right, let's go ahead and get started. So chapter 4.1, intro to differential equations. We're kind of throwing out a lot of different topics here in this chapter, chapter 4.1. We throw out the idea of differential equations. We're throwing out the idea of how do we process differential equations, which requires us taking the antiderivative. So this chapter is really more about, one, kind of telling you about the complexities of a differential equation, but then two, also how do we start thinking about, solving it with an antiderivative. If you haven't ever seen an antiderivative or an integral before, don't sweat it. We're actually going to spend the rest of the semester talking about it. And then you're going to learn a lot about antiderivatives and the whole process and the toolkits around them in calculus 2. Okay, so bear with me today when I just tell you what things are. you're going to learn it as we go. Okay, so let's talk about what is a differential equation. Okay, so differential equation is an equation that involves an unknown function y equals y of x, right? There's like y and then there's an x happening there. And its first or higher derivatives. So it's a combination of the function and its derivatives, right? So a solution to a differential equation, function y equals f of x, is a solution. It's a function that satisfies our differential equation. It seems a little hand wavy. We're going to get into some details about it. All right, so let's say, for example, a, b, and c are constants. They're arbitrary. They could be anything. Okay, so let's set up what things look like. So if I have an example differential equation, and what does its corresponding general solution look like? This is by no means an exhaustive list. This is just to kind of get you to think about things a little bit. There's a whole class on differential equations. There's a class just on differential equations, and then there's a class that combines differential equations with linear algebra in the math department, and they're good classes. I highly recommend them. Okay, so as an example, I can have y prime equals minus 2 times y. Just that these are all just like examples. Okay, so I've got my derivative equals some constant term times my function. That means my function must be some constant term times e, right? Minus 2x. So e, the function e is equal to its derivative, right? It's got some kind of constant term there. dy dt is another way of saying our derivative of y with respect to t is equal to t. My function y could be equal to 1/2 t squared plus c. C is some constant, right? We don't know. We have to have some kind of initial value problem in order to help us solve what that c term is. Same thing for here. We need like an initial value for that. Could say y double prime plus y equals 0. I think we did this back in chapter 1 or 2 when we were talking about trig functions. So my general solution could be a sine of x plus b cosine of x, right? So I take my second derivative and I add it to this function. It's going to be equal to 0. Okay, so each value of a, b, and c will give a particular solution. Right, and usually we need some kind of initial value in order to help us solve for a, b, and c. Otherwise, we leave things in terms of general. All right, so let's talk about a couple more things, how we classify differential equations. So we can classify differential equations in terms of their properties. The biggest properties are the order. The order denotes the highest derivative in our equation. Right, so for example, I've got y double prime plus y equals 0. My highest derivative, right, is my second. This right here is a 0th derivative. Our function is a 0th derivative. So this is second order. So let's write y, our regular function, equals the 0th derivative. Just as a nomenclature thing that comes into play a lot next semester. We talk about the 0th derivative. It's just the function. So the order tells us the highest derivative that's listed in our equation. The other thing is it linear or not? We're mostly going to be dealing with linear differential equations, linear properties. There are other non-linear ways of functioning, which we don't get into. It's beyond the scope of our class. So it's linear if it's written in the form like this. A sub n of x, y sub n. And let me write it out and then we'll talk about what things are. Okay, so so my a sub n minus 1, a sub 1, a sub 0, those are all functions of x, right? And that's equal to b of x. These are functions of x, okay? My y sub n minus 1, y sub n minus 1, etc. are all derivatives. Right, so I basically have a function of x times a derivative of y, okay? So I do not have terms like, I don't have y times y prime, or sine of y, or, you know, y prime squared, things like that, right? I don't have things that are going to be like, if y is a thing that I'm dealing with that has a derivative, right? I don't have multiple y's in terms of each term here. Okay, so let's do a table so you can see what some possibilities. This is like an example table. So I've got my differential equation, right? I've got its order, first, second, third, whatever. I've got whether it's going to be linear or non-linear. Okay, so let's do some quick examples so you can see what things look like. So y squared, oh, sorry, I just blew it right away. So this is going to be, sorry, ignore that. X squared, y prime plus e to the x, y equals 4. X squared y prime plus e to the x, y equals 4. So look, I've got y prime and y. So my highest order, my highest derivative is a first. It's a first order, right? And I have all functions of x multiplied by my y, so this makes it linear. Okay, let's try another one. I've got x y prime squared equals y plus x. Okay, so my highest derivative is my first derivative, so it's a first order, but I've got this y prime squared term. That's y prime times y prime, which makes it nonlinear. Like I said, we're dealing with linear equations in this class. Y double prime equals sine of x times y, y prime. So I've got a first derivative and a second derivative. My highest derivative is my second derivative. I have a function of x times my derivative, so this makes it linear. Second order linear differential equation. I can do y triple prime equals x times the sine of y. Now watch, look, I've got my highest derivative is my third derivative, but I've got a function of y times x, right? I don't want a function of y, I just want a derivative of y. So a function of y, so it's going to be nonlinear because of our sine of y. Okay. So we need to have some kind of process now for helping us think about how we're going to solve this differential equation. And that requires us doing like integration, finding the antiderivative. Like I said, bear with me. We're just going to roll through it, and then you're going to learn how to actually do it. Okay. So to actually solve a differential equation, we need a process called separation of variables. Okay, so separation of variables. it's going to look like we've got y prime equals some function of x, right? To get y equals, right? To get y equals something, I need the antiderivative. Right? So if this is a derivative, I need the antiderivative to help me go figure out what that function is. So the antiderivative looks like this. So y equals my antiderivative, my integral, like that. So to get my antiderivative, I need to separate the variables, right? Okay, so separate the variables. So it looks like this. So y prime, I'm going to rewrite y prime. So dy dx equals f of x times g of y, right? I could have some function of y, you know, like a y or whatever. So dy dx. So now what I need to do is I need to get all of the y's on one side and all the x's on the other. Okay, so I'm going to multiply by dx, I'm going to divide by g of y. So I'm going to go dy over g of y equals f of x, g of x. Okay, this is our method for separating the variables. Now to actually solve for this, right, I'm going to take the antiderivative of both sides. Okay, don't worry if you've never seen this before, you're not sure how to do it, you can't remember. We're going to cover it. We're going to spend a lot of time. The rest of the semester we're going to spend on it. Plus a lot of next semester we'll spend on it. Okay. So I've got my lecture examples for chapter 4.1. I'm going to start working through example number 1 using the separation of variable technique. And in this one, we're actually given an initial condition too. So we're going to use that to help us find things. All right, so y prime equals minus t times y of 0 equals 3. So I'm going to use separation of variables. Okay, so use separation. So I'm going to go dy dt. So y prime, I'm rewriting as dy dt equals minus t times y. Now I'm going to move my variables, bring y to one side, t to the other. So this becomes dy over y equals minus t times dt. Okay. Once I have all my y's on one side and all my t's on the other, I can take the antiderivative of both sides, right? Which is going to give me, you don't know this yet, we haven't learned it, so I'm just telling you things. The integral, the antiderivative of 1 over y is the natural log of the absolute value of y. Okay, and then I'm going to do what they call the power rule for integration. Don't worry, you haven't learned it yet. So minus 1/2 t squared, and then plus I always have to do a constant term. Okay, all of these things, how I just did this, right, is what we're going to be talking about for the rest of the semester, and also in calculus too. So don't sweat it, just take me at my word for now, and then we'll learn how to do it. Okay, now I want my answer in terms of y equals, not the ln of y, so I need to exponentiate both sides. Right, so this is ln, so I'm going to use e to the ln of y equals e to the minus 1/2 t squared plus c. So I've got a term here and a term here. When I do that, I can actually make this like it's, so e to the ln of y, I'm going to write this over here now. E to the ln, these are inverse functions of each other. So I've got the absolute value of y equals e to the minus 1/2 t squared. Right, this becomes times e to the c because I've got the same base. I'm adding the exponents. I'm going to separate this. E to the c is a constant, and we'll just call it c, big C, make it cleaner, right? It's just a number. So I can now say absolute value of y is equal to c times e to the minus 1/2 t squared. So here's my function, right? But now I'm going to use my initial value, right, to help me solve for c. Okay, so we're going to do that. So I'm going to say y at 0 equals c e to the minus 1/2 0 squared, and that was equal to 3. They gave me that, right? E to the 0 is equal to 1, so c equals 3, right? So I can put it all back in. So my y, my e is a positive function, right? So I can get rid of my exponent. So that's going to be 3e to the, I'm sorry, I can get my absolute value, 1/2 d squared. There. I don't need the absolute value anymore because e itself is a function that is always asymptotic to the x-axis, right? It's always a positive function. So let me write that down in a little color. We can lose the absolute value because e to the x is a positive function, right? Okay, so before we get into example number 2, we have to, I have to give you some background information for how that works, right? So what are the pieces of this one, how we can even set up the differential equation for that. So let's talk about water leaking through a tank. We always like these problems in calculus, right? So I've got this, since we're leading up to what we call Torricelli's rule, which I'm going to tell you in a little bit. So we've got water leaking through a hole at the bottom of a tank. There's a lot of geometry involved, like what's the shape of the hole? Is it square? Is it circular? Is it some weird function, right? If it's some weird function, I'm going to need to figure out the cross-sectional area using calculus. We're just going to, this example here is going to be all geometric. But let's draw our tank. So I've got a tank, looks like this. And then looks like that. And maybe I have some hole. It's creating a column of water, right? So I've got this, radius here, maybe, or some kind of a cross-sectional area. I'm drawing it as a circle, but I could have some kind of cross-sectional area. And I've got water that's up to a certain height. So this is my y. And then I have delta y. And I've got basically, there's a lot of preamble to the separate problems. So bear with me here as I write down all the little pieces and we'll discuss what things are. So there's a cross-sectional area. It's our horizontal slice of this. So that's whatever, if this tank is circular, then it's pi r squared. If the tank is square, right, it's going to be, whatever side squared, it's going to depend on the geometric shape that you're given. So always be thinking about the shape that you're given. Okay, and then because that cross-sectional area, we'll just write it as a of y. So now I've got a hole, right? So the hole has area, we'll just call it B. It's not B of y because it's just B. It's just whatever the shape of that hole is, okay? And it's got like a volume. The volume of the water leaking out, we can think about it in terms of water's pouring out in a column, right? So volume is going to be, right, essentially our base times our height, right? This cross-sectional area is our base times the height. So that's going to be base times the velocity of the water pouring out times the time it takes to pour out. I'm going to write down what all these pieces are. All right, so, so let's write this down. So V of y is the velocity. This is part of where Torricelli's law comes into play. Velocity of the water flowing through the hole when tank is filled to a height y. Right down B is the area of the hole, right? So this is velocity times time is going to give us distance, right? So that's our distance that that this water is traveling times the cross-sectional area. So that's how we're calculating the volume for that. A of y is equal to our area of the horizontal cross-section of the tank at height y. Let me let you guys finish writing that. I'm going to turn the page in just a sec. Okay, now we've got water exiting the hole. During our time interval, delta t, it's going to form a column, like a cylinder, of base B, and height, velocity times delta t, right? So that's our distance, right? So this is we've got a hole, the water's leaking out. We're just going to pretend that the water maintains that same basic shape. So velocity times time, delta t gives us that distance, and it's going to have that shape, the cross-sectional area of base B, okay? So the water lost during the time interval t to t plus delta t, right? That's our time interval that we're working out, can be computed in two ways. So the first way is taking a look at B times our velocity times our delta t. How much water, right, is coming out? It's approximately equal to that, right? And it's also approximately equal to the area of y times my delta y. This is water level drops by amount delta y during time period delta t. Okay, then this is our volume. Okay, so this is happening during t to t plus delta t interval. Because we've got two different ways. Now they're both like approximate, right? So what I can do is I can set up essentially like a ratio of these two, and it's going to help me figure that out, because the cross-sectional areas may not be constant, right? Maybe that our tank is shaped like this, right? So that our cross-sectional area changes as a function of height, essentially. So I can say, a delta y is approximately equal to bv of y delta t, right? Because we've got these two different ways to be able to do it. So I can set them equal to each other, right? And I've got delta y delta t, change in y over the change in t. This is a lot of preamble to give you background for how you're thinking about these types of problems. Okay, so delta y over delta t is like bv y all over a of y. Okay, now this is like if we take the limit of delta t as it approaches 0, right? Then basically what we're going to get here is dy dt equals bv of y over a of y. Okay, v of y here is where we have Torricelli. Okay, so Torricelli's law helps us deal with the velocity, right? So let's go ahead and write it down. I didn't want to just give you the equation and say, go ahead and have at it. It's helpful to kind of think about where all these pieces come from. So Torricelli's law deals with our velocity. So the velocity is equal to minus square root of 2 times the gravity times the height times y, the height that we filled it up to. So let's fill it up. We'll do it in metric units. So minus 2 times 9.8, that's meters per second, times y is going to give us approximately minus 4.43 radical y, and this is in meters per second, right? If we do this in English units, we're going to use 32, okay, and then we're going to have feet per second, but right now in the metric system, we have minus 4.43. Okay, so that gives us, Torricelli's law gives us our velocity relationship. So the velocity, right, of the water pouring out is going to be proportional to the height that it was filled to. All right, there's a lot of setup. Right, we're going to go on to example 2. We're going to fill out a lot of this stuff here, and this is going to help us, right? Torricelli's law is going to help us set up, answer this question here. All right, so cylindrical tank. So I'm going to start drawing this out. It's a cylinder. I've got a radius of 1 meter, and it's a height of 4 meters. It's filled with water. So the water is basically, you know, filled like that. Water drains through a square hole. So the square hole of side 2 centimeters, okay, in the bottom of the tank. Oops, there you go, 2 centimeters in the bottom of the tank. Determine the water level. How long does it take for the tank to go from full to empty? The water level, this is gonna be the bulk of our problem. This is coming up with the equation. We're gonna use Torricelli's law and that relationship, that ratio, right here, this dy dt, b, v of y, a of y, plugging in what v of y is right here, right into this equation. That's going to give us our differential equation. But first, let us set it up. Okay, I chose to do things in terms of centimeters. You can leave it in meters if you want. Just make sure, watch out, this is in centimeters. These are in meters. So make sure that your unit, you do a unit conversion so that things are consistent with each other. Okay, so so y of t, this is the height of the water. Okay. All right, so let's go ahead and do it. So the first step, step 1 is going to be, we're going to write down and solve our differential equation. And we're going to use that ratio and Torricelli's law to help us do it. Okay, so the first thing I need is, I need the horizontal cross-sectional area. It's a circle, right? So my area, it's just pi r squared, right? And my radius is 1 meter. Well, it's 100 centimeters, right? So it's going to be pi times 100 centimeters squared, okay? Which is going to give me a of y is equal to 10,000 pi, okay, centimeters squared. Okay, so that's A. My next bit, okay, I have to do the area of the whole area, which we said it was a square. So B is equal to the side squared, which is equal to 2 centimeters squared. So that's equal to 4 square centimeters. Okay, so that's our B. Okay, and now our gravity, let's just write it down, our gravity. We're in metric, right? But I'm doing centimeters instead of meters. So this is going to be 980 centimeters per second squared. Okay, so I'm going to use Torricelli's law. For my velocity. So it's going to be minus radical 2 times 980 times y. So it's going to give me minus 44.3 radical y. And this is in centimeters per second. That's my v of y. So this was all kind of set up, right? And now my differential equation is dy dt equals, remember we did before, v over a of y. So I'm just going to plug in the pieces that I have. So b times v of y. So b is 4 times minus 44.3 radical y all over a pi. Okay. This was I divided through by pi, so I got like an actual decimal. So I got, it was equal to minus 0.0056 approximately radical y dy dt. So this is my differential equation. Okay, so I need to use separation of variables to help me solve that. Okay, let you guys finish writing that. I'm going to turn the page and then we're going to do separation of variables. Okay, right, so separation of variables. Okay, so let's write down our equation first again. So I've got dy dt equals minus 0.0056 times radical y. So remember, separation of variables says I have to put all the y's on one side. dy over radical y, and all the t's on the other, minus 0.0056 times, oops, dt. Okay. So to solve for y, I find the antiderivative, right, which means I'm going to go dy over radical y. You don't know how to solve these yet. I haven't told you how to do that. As usual, we're giving you the answers before we teach you the skills, right? But we're going to spend a lot of time on how to do it. So take my word for it now. So this is going to give me 2y to the 1/2 equals minus 0.0056 times t plus c. Okay, so how I got from here to here, don't sweat it for now. Take my word for it. We're going to cover this a lot, how we got from here to here. Okay. All right, so now I need to solve for y. So I'm going to divide both sides by 2, and then I'm going to square everything. So I did some algebra to solve for y. So I've got minus 0.0028t plus 1/2 c squared. 1/2 c is just a constant also. So I'm going to rewrite this as c minus 0.0028t squared equals y. Okay. Now I have to figure out what c is, right? I have to use some initial condition information to figure out what c is. C is just a constant. So it doesn't matter if I multiply, divide, or whatever my constant, it's still a constant. Okay. All right. So now step 2, use initial conditions to solve for c. All right. So let's think about our initial conditions. So we're going to say the tank, we're told the tank is full at time t equals 0. At the beginning, when we first start, tank is full, okay? Which means that my y of 0 equals 400 centimeters, right? That's my initial height. So I'm going to go y of 0. So 400 centimeters equals let's see, minus 0.0028t plus c squared. Okay, so this is a 0. So this becomes 400 equals c squared, right? Because it's t is equal to 0. So I take the square root, I take the square root. I'm going to get c is equal to plus or minus 20. So which c, the plus or the minus, is correct? Because I can't just write an equation with both. I have to think about it, right? So I have to think about what's actually happening here. So let me logic my way through it. So, oops, sorry. So our water level is decreasing. So this is water level y, is decreasing as a function of time, right? We start off with a full tank. As time goes on, our tank gets less and less full, right? So our water level y is changing, it's decreasing as time goes on. So that means our function y equals c minus 0.0028t squared, right? Decreases to 0, right? So this thing decreases to 0, but the only way it's going to decrease to 0 is if I have a positive number when c is positive, right? Y is always going to be positive because we're squaring this value, but think about what's happening here. If this is a positive, 20 minus this number here, 0.0028t, right? 20 minus that differential is going to get smaller and smaller and smaller when 20 is positive, right? I'm going to square it. If 20 is negative, I'm going to add these two together. It's going to get bigger, right? So it only happens when c is positive. So therefore, our equation is y is equal to 20, or positive 20, minus 0.0028t squared. So that's our equation. Okay. The second half of the question was, how long does it take for this thing to become empty? How long until the tank is empty? We can say it happens at time t sub e, which is, it's like time when the tank is empty, time t sub e. I guess I'm going to go y of t sub e. So when the tank is empty, my height of the water is 0, right? It's empty. I don't have any more water left. So this is 20 minus 0.0028t squared. I'll put a TE here. Then I'm going to solve for t sub e, right? So I square root both sides. I solve for t. I'm going to get t sub e is approximately equal to 7,142. Watch out, that's in seconds. Oh, it seems like such a long time. But if I convert it to hours, that's like approximately 2 hours. So it's not so long. 2 hours. I'm not writing this very clearly. Okay, so 2 hours. Okay. Right, so that's how we set it up. So there's some things in there that we did that you guys haven't learned yet, like how we take antiderivatives, but we're going to start doing that on Thursday. Actually, we're going to start in with chapter 4.2, which is also chapter 1.1 in our integral calculus book. Remember, we don't have school, we don't have classes on Wednesday because it's a holiday, so we'll pick up again. I'll talk about answer any questions you guys have for homework on 4.1 on Thursday if you want. 4.1 will not be on the quiz. Okay, it'll be on the quiz next week. Okay, we'll have a quiz this week on chapter 3.5. Okay, guys. Have a great day.
Thank you.
Thank you so
Bye.
much.
Thank you.
Thank you.
Bye.
Thank you.
Bye. Take care.